Before we start, check this out. This was the stuff from before. If you scribble over it, it goes away. I thought that was pretty cool. Okay, now this video will be much less important if you're looking at the grand scope of the course and what might come on examination. So you didn't hear this from me, but if you're cramming for the exam, you can probably skip this video. But it is very important, so don't skip it unless you really need to. So the question we're going to ask here, we figured out this whole discrete cosine and sine thing last time. Now our question is, in the real world, if we have a continuous signal, okay, so a continuous cosine or sine with frequency, let's call it f naught, we want to know what does that look like in our discrete slash sampling slash what does that have to do with our world where we're taking like snapshots of this signal? Okay, so let's start by defining this thing in the first place. So what does a continuous signal with frequency f naught looks like? Well, it looks like x of t, so now we're in continuous time, is cosine of 2 pi f naught times t. And you can convince yourself of this. How? Because just remember the rule that the period is 2 pi over whatever comes in front of the variable. So 2 pi over 2 pi f naught, which is 1 over f naught, right? If that's the period, then the frequency is 1 over the period, which is 1 over f naught, which is f naught. So this is a cosine with frequency f naught. Okay, so that's all set and done. Okay, now the question is how do we relate this to our discrete version? And the important thing to realize is that all we're doing is when we discretize a signal, so when we turn this continuous signal into a discrete signal by sampling it, we are just taking time and splitting it into chunks. How do we do so? We split time as follows. We in the continuous world, in the discrete world, we do what? We sample every TS seconds. Okay, so TS is 0.5 seconds. That means every 0.5 seconds, I'm clicking a button and I'm saying, hey, record the signal at this point. Hey, record the signal at this point. And I push that button every 0.5 seconds. Okay, so what's the relationship between the actual, so the relationship that kind of bridges these two worlds is little t equals n times ts, right? And it's quite an important relationship. It says that the time that you're at in the real world is the sample I'm on, sample number 5 maybe, times the amount of time it has taken for each sample. So that's a very nice, that's a pretty clean, like intuitive formula. And so, right, what does our x of t kind of become? Oh, well, x of t was initially cosine of 2 pi f naught t, but we know t is nts in the discrete world. This becomes cosine of 2 pi f naught times nts. Okay, quickly let's rewrite that to make it a little bit cleaner. 2 cosine of 2 pi. I'm going to use the fact that I know also that in the discrete world, right, ts equals 1 over fs. So just this is the classic t and f relationship, period and frequency relationship. If I sample every 2 seconds, then I'm going to have 1 over 2 cycles every second. Or 1 over 2 samples per, like 1 over 2 samples per second. So that's what our frequency is. Let's replace ts with 1 over fs, so we get 2 pi f naught over fs n. Okay, that's our signal now. And remember, we're trying to see what's the discrete frequency. So now that this is discrete, right? It depends on our little n, which is discrete. It's going from like n equals 0 to 1 to all the way big N minus 1. That's our classic, right? Now we can match this to our normal discrete cosine, right? And our normal discrete cosine is cosine of 2 pi k little n over big N. But I'm going to write that a little bit different. I'm going to write that cosine of 2 pi k like this. So we can match these two with each other, and we can say that, hey, the n's and n's are the same, so this guy has to equal this guy. So you say, okay, 2 pi f naught over fs has to equal 2 pi k over big N. 2 pi's cancel out, and we get the relationship which says that we want to solve for k, right? We want to solve for a discrete frequency. It says that k equals f naught over f naught over fs times big N. Okay, and this is really the key relationship. It says if your actual signal has frequency f naught and you sample with frequency fs this many times, this is going to be your discrete frequency. And it's a good relationship to have. This leads way. So you could do this with an example, and you can make up an example and see how this plays out. I'm not going to spend time doing that. But just to, again, reiterate, this brings back the point that if an important rule that says if I sample at fs, okay, so if I fix my sampling frequency to be fs, that means I'm saying I'm going to sample, I'm going to push the button a certain amount of times per second, okay, and I'm going to call that fs, okay. The highest or the maximum continuous time frequency you can get is fs over 2. Let me make sure the ordering is right. So if you sample at, for example, at maybe 10 per second, then the highest frequency you can sample is 5. Okay, and the reason why, it doesn't matter how many times you sample it. That's kind of a fundamental limit. And the reason why is because what happens when f naught is fs over 2? So when your actual continuous time frequency is your sampling frequency divided by 2, what happens to k? Well, k equals f naught, which is fs over 2, divided by fs times n, which becomes n over 2. And remember, we said when k is n over 2, that's like if this is your n, right, and this is your n over 2, this says that you have n over 2 oscillations, which is again, just take the example of like 8, right? 8, even let's do n equals 4, right? So 1, 2, 3, 4, 2, 3, 4, right? Maybe a fourth one. What's the max you can fit here? Well, the maximum you could fit is 4 over 2 equals 2, right? If n equals 4, the max oscillations, the max k we can fit is 2. Because you could put 1 positive here, negative here, positive here, negative here, positive here. So that's 1, 2 oscillations. We can't fit more than that because we're just not sampling fast enough. Okay, so when f naught is fs over 2, we hit this maximum, which means any higher than that, and this thing will get too wiggly, and we won't be able to sample it properly and get the whole signal properly. We'll lose some information from the signal. Okay, so in real life, this usually works the opposite way, right? Because in real life, you're never really given an fs. You're given the frequency at which you're trying to sample. Okay, so this says that if for whatever reason, like let's say you're trying to sample a note that's an A. So I think A is like 420 hertz or something like that. Okay, if you're trying to sample that, at minimum, your fs needs to be 2 times f naught, right? Because here we said f naught is fs over 2. That means fs equals 2 f naught, which means you have to sample at a minimum rate of 840 hertz to capture the whole signal here. Any slower than that, if you do like 800 hertz, it's not going to work. You're going to lose some of the signal, okay? And this is like a fundamental property. It's called like the Nyquist limit or something like that. But it kind of makes sense if you just walk through all of the calculations. So yeah, that's pretty much the end, I think, for the most part. That's the end of like the intro to discrete signals unit. So hopefully this was like a good introduction, and hopefully you have a wonderful day.